Good day everyone. Today we're exploring one of the most exciting frontiers in technology, quantum computing, a breakthrough that could completely transform how we solve complex problems. As our demand for faster and more powerful computing grows, quantum computing emerges as a potential game changer. Unlike traditional computers which are reaching their physical limits, quantum computers promise to solve problems that would take even today's supercomputers million years in just minutes. Let's rewind to the 1980s when the idea first took root. Physicists Richard Feynman and Yuri Manin realized that classical computers struggled to stimulate quantum systems accurately. Feynman proposed a bold idea: to build computers that used the very rules of quantum mechanics. In 1982, he formally introduced the concept of quantum computer. Then in 1985, David Deutsch introduced the quantum Turing machine, the first theoretical model showing how quantum computers could outperform classical ones. But it was Peter Shor in 1994 who truly shook the world of computing. He developed an algorithm that could factor large numbers exponentially faster than any classical method, threatening the foundations of modern encryption systems like RSA. These breakthroughs turned quantum computing from a wild idea into serious scientific pursuit. To understand why quantum computers are so powerful, we need to compare bits and qubits. In classical computers, a bit can either a 0 or a 1, like simple switch that's on or off. But a qubit or quantum bit behaves differently, thanks to a property called superposition. A qubit can be both 0 and 1 at the same time. Imagine a switch that's both on and off simultaneously. This ability to hold multiple states is what allows quantum computers to process vast amounts of data in parallel. And there's another quantum twist: entanglement. When qubits become entangled, their states become linked. So if you change one, the other reacts instantly, no matter the distance. This allows quantum computers to process and share information in ways that classical computers simply cannot. In short, quantum computing is just a faster computer. It's a new way of thinking about computation. By harnessing the strange but powerful laws of quantum physics, it opens the door to solving problems that once seemed
First
impossible.
are the technical limitations. At the heart of quantum computers are qubits, which, unlike classical bits, it can exist in multiple states at once. However, qubits are extremely fragile. They are highly sensitive to changes in temperature, vibration, and electromagnetic interference. This makes them prone to decoherence, which means they lose their quantum state quickly, leading to major computational errors. In addition, quantum gate operations, which process information, often suffer from inaccuracies, adding even more errors and reducing the overall reliability of quantum calculations. For the second major issue is cybersecurity. Quantum computing introduces the possibility of breaking existing encryption systems. Algorithms like Shor's algorithm can factor large numbers much faster than classical computers, threatening commonly used encryption methods like RSA. This poses a serious risk to sensitive data, financial systems, and national security. Without the development of quantum-resistant cryptography, governments, institutions, and individuals could be vulnerable to massive data breaches. In summary, while quantum computing is revolutionary, its technical fragility and cybersecurity implications must be urgently addressed before it becomes safely and widely usable.
Quantum computing has the power to solve problems that the classical computers can't handle. However, despite its promises, major challenges still prevent the widespread use of quantum computing today. One big challenge is error correction. Heat, noise, or even small vibration can easily disturb qubits, leading to errors. Unlike classical bits, fixing error in qubits is much harder. Correcting one qubit may require many more qubits just to keep the system stable. This makes the technology more complex and harder to scale. That leads us to the next challenge: scalability. Today's quantum computers only operate with a small number of qubits, but to solve real problems, we need hundreds or thousands. Scaling is tough. There are technical difficulties like controlling the qubits, preventing interference, and maintaining ultra-cold temperatures. All of this adds to the cost and difficulty. Then, there are hardware and software limitations. There are no standard hardware yet. Some use superconducting qubits, Others use ions or photons. Quantum programming differs significantly from our familiar software. It's difficult to write, test, and run quantum code because tools and experience are limited. Adding to that, there's lack of standard and protocols. Since the field is so new, there is no universal way to measure or compare different systems. This slows down collaboration and make it difficult to track progress across platforms. And we also face a talent gap or educational gap. Quantum computing requires knowledge in physics, math, computer science, and engineering, but very few university offers full programs in quantum tech, leading to shortage of experts. All these factors lead to high development costs. Quantum research needs special labs, top scientists, and long-term investment. Because it's still evolving, it's high-risk venture that not all investors are willing to support. In summary, quantum computing revolutionized our world, but we need to overcome this technical and systematic barrier first. With continued research, education, and collaboration, we can bring this powerful technology into the real world.
And now, for the major trends that are happening on the field of quantum computing. So first, one of the key trends today is quantum machine learning or QML. It combines quantum computing with AI to make data processing faster and more efficient. Unlike traditional computers, quantum systems can explore many solutions at once using superposition and entanglement, allowing machine learning models to train and make predictions much quicker. QML is being used in areas like drug discovery, climate modeling, and economic forecasting, where handling large, complex data is crucial. Countries like the United States, China, India, and Australia are heavily investing in this field, signaling a global race toward quantum innovation that could transform industries, including industrial engineering. And for the next trend, quantum programming is becoming more accessible thanks to open source tools like Qiskit, Cirq, and PennyLane. These platforms allow more students and professionals to explore and develop quantum applications. We're also seeing a significant rise in educational programs and quantum development courses, which help prepare the next generation of quantum engineers. Another key trend is the strengthening of industry academic partnerships. These collaborations are helping translate quantum research into real-world applications, paving the way for innovations in fields like manufacturing, logistics, and healthcare. In 2019, Google demonstrated quantum supremacy by solving a problem in just 200 seconds, something a classical supercomputer would take 10,000 years to complete. This milestone highlighted how powerful quantum computing can be. Now, if we look at the diagram, we see a clear comparison between classical and quantum computing. In classical computing, we write code in languages like C or Java, compile it, and execute it to get binary outputs, basically fixed zeros and ones. Quantum computing, on the other hand, works differently. Instead of traditional code, we design quantum circuits, compile them for quantum hardware, and use classical optimizers to fine-tune parameters. The outputs are probabilistic, so we evaluate and refine the solution repeatedly until it converges. So this comparison reflects a major current trend in quantum computing, hybrid systems. So this combine classical and quantum resources to solve problems more efficiently. Hybrid computing is especially useful now since quantum systems are still limited. It's already being used in areas like logistics, production planning, and facility layout, where even small improvements in optimization can make a big impact. And now for Chapter 3, which are the implications of quantum computing within the field of industrial engineering. So this topic directly supports our field in several ways. First, it improves optimization by using quantum algorithms to evaluate multiple solutions at once. This is useful in tasks like production scheduling or route planning, where traditional methods take longer to find the best option. Next, it enables smart systems by integrating real-time data and AI. In an industrial setting, this means machine can adjust operations automatically. For example, adjusting conveyor speeds based on demand or detecting equipment issues before they cause downtime. It also boosts decision-making by using advanced simulations that account for uncertainties. In manufacturing or healthcare, this helps determine the most efficient use of materials or staff scheduling, reducing waste and increasing productivity. Quantum principles like superposition and entanglement are applied through quantum computing, which allows us to model complex systems like supply chains with greater accuracy by processing many variables at once. Lastly, as these technologies grow, industrial engineers can take on new roles in areas like quantum-based logistics, smart factory design, and technology integration, making us more prepared for the future of industry.
Quantum computing is expected to transform the roles and responsibilities of industrial engineers. Traditionally, we are called to improve systems and processes, but with this emerging technology, we'll be required to adapt entirely new tasks, skills, and roles in advanced computing. We will need to work with quantum tools that can solve highly complex optimization problems, far more efficiently than classical computers. This shift means we'll see new career paths, such as quantum systems integration specialist, quantum optimization analyst, and hybrid computing engineer. These roles won't exist in isolation. Industrial engineers will work closely with quantum physicists and software developers to apply quantum algorithms to real-world challenges in logistics, manufacturing, aerospace, and even healthcare. Around the world, governments and private industries are heavily investing in quantum. For example, Australia is investing over 1 billion in quantum technology, aiming to create nearly 20,000 jobs by 2045. Meanwhile, US states like Colorado are establishing national quantum hubs, showing the increasing demand for quantum illiterate professionals. As quantum computing matures, industrial engineers will help integrate quantum systems into enterprise solutions, optimizing supply chains, enhancing security and scalability, and making manufacturing systems more cost-efficient. Studying quantum computing gives industrial engineers a competitive edge in next-generation industries. Core skills include understanding key principles of quantum mechanics like superposition, entanglement, and decoherence. On a more technical level, we learn to use quantum programming languages such as Qiskit or Cirq, design quantum algorithms, and get familiar with quantum hardware platforms. One of the most valuable applications for IEs is quantum-enhanced combinatorial optimization. This includes high-impact areas like job shop scheduling, facility layout, and transportation planning, tasks that are often too complex for classical systems to solve efficiently. Beyond optimization, quantum-enhanced AI is another exciting area. It allows to develop more accurate, predictive models and improve smart manufacturing systems, essential for Industry 4.0. To do this, we need to combine knowledge of classical AI with quantum machine learning. There's also a global talent gap in quantum engineering. This opens the door for industrial engineers to bridge the gap between domain-specific expertise and quantum computational skills. Platforms like IBM Quantum make this learning accessible by allowing us to run real quantum simulations and gain hands-on experience, even as students.
On our research, quantum computing stands as one of the most transformative breakthroughs in information and communication technology. Its core principles, superposition and entanglement, allow it to process complex problems at speed far beyond what classical computer can achieve. This gives quantum computer a unique edge in solving tasks once considered impossible. However, despite its promise, quantum computing is still in its early stages. It faces serious challenges, including scalability issues, fragile qubits, gate errors, and cybersecurity threats. There is also a lack of standardized systems and limited educational infrastructure. But even with these obstacles, global research and investment continue to grow rapidly, highlighting the technology's incredible future potential. In industrial engineering perspective, quantum computing has the power to optimize operations, improve logistics, and strengthen data-driven decision-making. It opens doors for predictive analytics, waste reduction, and productivity maximization of critical components for smarter and more sustainable systems. In conclusion, quantum computing equips future industrial engineers with advanced tool-led innovation. As the field progresses with research, collaboration, and education, it will become a powerful force in transforming industrial systems worldwide.